is absolutely symmetric. Very good symmetry. And then delta V the same, or can you say but same direction or no? Yeah, opposite direction, same value, and we call this differential input, right? And what else do you remember? Good, small signal or linearized circuit, right? So it need to be linearized. So, which is always correct in this class because that is our goal, but will not be always linearized. Same when you design your circuit, right? So we will not prove it again. We proved it last time, but then we look at this one. We say this one goes up and this one goes down by the same amount. And here we assume R1 equals to R2. So they're symmetric about here. And it's just resistor. So it's linear. Even I have a large signal, doesn't matter. It's still linear, right? So then I can say Vx equals to 0, virtual ground. Okay, it is not connected to ground, but it's always 0 in AC signal, right? Or in this case, it doesn't matter to be AC, right? Similarly, for the differential pair at the bottom, if I apply a small signal, delta V to the left and negative delta V to the right, they are small, so I am doing small signal so I can linearize the circuit, so it's linear. Second, if I do a cut along this plane, I see that they are absolutely symmetric on the left and right. In order to make it absolutely symmetric, M1 need to be equal to M2. But you also need to bias them exactly. So they need to have the same common mode voltage. So this need to be, if this is 2 volt, this need to be 2 volt. If this is 3, this need to be 3. If you bias this at 2 and this at 2.1, even you apply the same differential signal, right, increased by 10 millivolt and decreased by 10 millivolt, it is not absolutely symmetric. Then you cannot use the virtual ground concept. But in this case, I can use it because of what I said. So on this plane, this is grounded, this is also grounded, right? And then the rest is easy. Any questions? Now, if no, then let's go to a new topic. After we have learned this, right? So let's do something very difficult. In E122, when you see this, I ask you to find a gain, you will just draw the small signal. And then you spend the whole day to do it. And I'm sure that you cannot do it, I cannot do it either, right? Because 4 transistors are lots of equation. Now, based on what we have learned here, first of all, we are dealing with small signal. So we assume this is linearized. Second, we assume it's symmetric. I mean M1 equal to M2, M3 equal to M4, right? And then we assume we have a differential input. These are given. Either I give you or you figure out, or you are the designer, you decided to operate in the small signal regime. How should we solve this circuit now? Separate. So because I really want to use the virtual ground concept, so I know this is grounded. Because it's symmetric, right? Remember, the connection need to be symmetric also, right? Okay, so you're very fast, but let's draw the circuit first. So when I separate it, it becomes this circuit. Do you agree? How about the other half? How should we treat it? Same. I just put it aside, right? But then the result is the same, right? Why do I want to draw it? All I want to know is just what is the gain here. Because the differential input give me double input, and then the differential input will double the output. So the gain of this whole circuit is just the gain of this circuit, right? So now we will start asking ourselves, do I need to solve the small signal, or I already have something in my cheat sheet? What type of amplifier is this? Someone say common source. Let's do it step by step. First, the one on top is diode connector. Very good. The one on top is PMOS, right? So let me label them. This is source because PMOS has a higher potential as source, right? This is drain, this is gate. And gate is connected to the drain. So yes, you're right. This is diode connector. So it's just like a resistor. The bottom one is NMOS. So this is source, this is drain, right? Because the source connected to the lower potential. And this is gate. So input is to gate, output is to the drain, from the drain. And then the source is grounded and is loaded by something called diode connector. And as a result, what is the gain? This is a common source one, right? But now can you substitute with what we have here? Which GM? GM1, very good. Because GM1, M1 is the one that get the inputs, right? Then how about what is RD? RO2 parallel 1 over GM. Okay, this is free here, by the way. So let's call it free. RO free, right? The one is free, yeah. All right, excellent. So you do need to know this, right? So very good. This is RD, right? So you do it step by step. We solve this complicated circuit in such short time. But sometimes it's not that we solve it fast. On the other hand, is that you see this, you can design a circuit from there. Right? Even you know how to solve it very fast using KCL, KVL. You don't have the insight. I ask you design a certain differential amplifier. You cannot get that. You cannot do it by thinking about KCL, KVL. But now you can just naturally, if you can design this common source, you know, I can just hook up to become a differential pair, right? The gain. Now this is the gain of this part, right? But however, when I consider the differential input, the V in is going to be double, correct? But V out will be double also. So that the total gain is still the same as the single side. Very good. Okay, how about this one? Right, very messy. But the first thing now, we know that this class is about virtual ground. So you know I am assuming it is symmetric. I'm assuming it is small signal. I'm assuming that, what else? Differential input, right? Okay. Now we need to see whether it's symmetric, right? Or we need to find the plane of symmetry, okay? I claim that this is the plane of symmetry. Do you agree? Is this symmetric? No. If you...
The current sources are shared between the drain sources of VN1, VN2,
Okay.
MOSFETs, and then SS2 is shared at point Q. So even though that P is drawn on the left, it is in fact symmetric.
Very good. Yes. So the first question say that the first one you answer that it is not. You are also right. You say that it's not symmetric. Indeed, in drawing, it's not symmetric. However, what we care is not how you draw it. What we care, right? For example, if I draw a differential pair like this, is this symmetric? In drawing, it is not, right? But from electrical point of view, if you were the electron, you feel the same thing. So this is the same here. This one, although it's drawn on the left, but from the topological point of view, the distance from here to here is the same to here, unless you tell me that this wire is longer than here and you have more resistance. But in our case, we assume this is an ideal wire, so there's no resistance between them. So as an electron, you feel exactly the same thing when you are at point P, left and right. Okay, is this okay? Okay, so say again. You're right. If it has resistance, then it's not symmetric because then I have a larger resistance here. But what I'm saying is that now we assume all these wires are ideal, no resistance. Right? So that is a good point, right? So we assume no resistance. So this is symmetric in this sense. Here it does not. Yeah, here it does not touch. So be careful. Let me remove this line. The Q, ISS is only connected to Q. Okay, and here this one is only connected to here. Okay. Okay. Just yeah. Okay. Yeah. So this is a bad drawing. But anyway, the industry standard. Yeah. If you
Microsoft Word, so you can get the Pro subscription.
okay, if you're VP, you can draw whatever you want. But if your VP don't like it, yeah, that is. But anyway, even that connector is still symmetric. Okay, but anyway, this is the main point. You identify this is the plane of along the plane of symmetry, along the plane of symmetry, along the plane of symmetry, right? And you can put anywhere. You should be able to put here or wherever because the result should be the same if there's no wire resistance. So I'm going to ground this one, which is not surprising because VDD needs to be grounded anyway, right? I'm also to ground this one, and this is AC. I always open the current source. So then I will see that this becomes this. And of course, current source need to be changed, right? Removed, right? So don't panic. Let me just draw whatever we have first and then see what we can do. I have V in here. And I forgot to label the transistor. This is M1. Let me call it M1. This called M2. And this is grounded because this is at P. Okay? Then this is connected to M3. And this is grounded because it's connected to Q. A little bit messy. If you look at this without knowing that we are doing AC signal, you will see that this is not a circuit, right? You only have everything connected to, this is floating and whatever. The reason we get this because we're doing AC analysis. And we know that this is properly biased. They are all in the saturation. Now, if you were going to solve the KCL, KVL, you will find that, isn't that this is the same as trying to solve this problem? I still keep V in here. I keep M1 here. But I have the liberty to draw it in this way. And now I don't know how to draw it.
That looks awfully a lot like other source.
So I'm going to erase this so those who only read the slide won't get confused. All I did is just flip it, right? In your lab on the bench, you just move the TA asks you to move the whole block to the left. That's it, right? And now you said that looks like a common source. it is indeed a common source, exactly the same for small signal. Because on the top, I need to ground it anyway, RD. This is like RD, right? On the top, I need to ground it. Yes, this in here is actually going to ISS, but in small signal, it is ground. A common source need to be ground. I don't claim it this is a common source, but if I solve the KCL and KVL, the equation should be exactly the same as if I was solving a common source, right? Then why do I want to solve it? I just recognize that the impedance of this guy will act as if it's the RD, right? If this were the RD, then I will get the same result, right? So the gain must be again equal to negative GM RD. But what is the GM in this case? GM1 or GM3? GM1, because this is the transistor which get the input, right? What is RD in this case? Very good. RO3 parallel 1 over GM, because right at the beginning, some already told me that this is diode connector. I flip it up, it is still diode connector, right? The topology does not change. If you don't trust me, you try to solve it. This is just a small signal for a diode connector, right? And what is the RO in this case? RO1. So we get exactly the same. Hold on, did I do something wrong? Oh, assume no channel. Yeah, that's why it's different from my cheat sheet. Okay, so assume no channel link, no CLM. Then what would this be? Negative GR1 over GM3, because RO3, RO1 is infinity, right? So yeah, then I'm right now. Okay, is that okay? Yeah.
Just to confirm,
Yeah.
the negative GM1 over GM3 is for the left side only. But if we take V out,
Yeah.
it's twice. But then it gets divided by 2.
Yes. The output will be twice, but the input will be twice also, because you have differential input. Yeah. Right. So remember, when you use this method, the total gain is the same as one side gain. Yeah. On the other hand, I did not talk about this negative. Whether it's negative or positive, when you're doing differential pair, I will give you the same score. I won't deduct the score unless I clearly define what is V out. Because you can take V out on the left plus, right minus, or on the right plus, left minus, depending on how you use it, right? That's the good thing about the differential pair. For a common source, you always get negative gain, right? But for differential pair, you just rewire it, then it becomes positive. Okay, so I keep it negative because we're looking at this common source. But if you make it positive, it doesn't matter because we're talking about the differential output. Make sense? Yeah, that's a good thing about the differential output. Another question. How do we do this? Assume differential input, and I think this is a symmetric, right? The point is I need to break it into a two parts. How would I break it so that it's symmetric? Yes. Any other ideas? Do you agree with him? Split it. Yeah. And in the lab, what will you do? Just cut it, right? Indeed, you need to cut it, okay? So then why I want to say that? Because just like what you said, then after you cut it, what you get is half of the resistor. Okay? So you have RDD, which is just equals to, right? Although this is trivial, but you need to be very clear, otherwise you may make mistakes. No, I should not put the ground now, otherwise you thought that they're the same. Yeah? The top and bottom are the same. So when I cut it, I cut from here, it's the same as I'm cutting from here. Okay, so because of this, then of course I'm going to take off the current source again. They are not in, they are DC, so they are open in AC, and then just follow it carefully to draw it. We out, we in, and this is grounded because, oh no, this is not grounded. Where should the source go? Go through the resistor. Which resistor? Thank you. RSS divided by 2. Not RSS, but RSS divided by 2. Then how about the drain here? RDD divided by 2. Okay. And using what we learned before, this can be flipped to the top. Again, it's just a common source, but with what? Good. With degeneration, right? So you got CS with degeneration. And the gain in a CS with degeneration, if you forgot, is just equals to GM times RD divided by 1 plus GM RS, right? Am I right? What is GM in this case? M1, right? And what is RD in this case? RDD over 2 and plus GM1. What is RS? SS over 2. Very good, right? So, yeah, I'm right. That's it. Right? So, if you look at this circuit, it's so complicated, particularly the current source make you so confused at the beginning. Right? If you're nervous, you're in rush, you feel that you cannot do it. But you break it down slowly, gradually, eventually it's just a matter of finding the equation from your cheat sheet. Okay. Let's do one more, right? This one is Cascode differential pair. We have learned Cascode circuit before. Cascode circuit means that I have the, maybe I can remind you a little bit. What is a Cascode circuit? We have the, maybe this is the current source. We stack another voltage on top of it, which is a biasing voltage. And then we put the input to here, right? And then we have the V out. Do you still remember what is the gain? If I call this M1, M2,
same thing, except it's got to multiply by the.
approximately, you don't need to give the whole thing, but remember, compared to common source, what is the difference between Cascode? Low over 1 over GM2RS, right? But just compared to common source, that is common source with degeneration. But common, what's the gain of common source? Yeah, negative. We say let's just call it, if I have ideal loading, right? So it's just GMRO. Now Cascode, what is that? Why is so great? Square. It becomes GMRO square. Or on the other hand, we can say that this is like approximately equal to GM1 RO1 GM2 RO2, which is GMRO square, if they have the same magnitude, like same order of magnitude. Okay, so let's come back to this circuit. Again, this is easy to find out if this is symmetric. I just cut it here. And yeah, M3 equal to M4. It is given. M1 equal to M2 given. So it's symmetric, right? So I'm going to put a virtual ground here. Virtual ground here. I'm still going to remove this, right? So this is just a Cascode circuit. V in 1, VB1, M3, M1, grounded. So the gain is just equal to what I show here, right? If you want to have the full gain, is GM1 and then the total resistance. Not actually, this one is still not the full gain because our GM1 assume that there's no channel length modulation, if you remember. But a more complete one will be, then the output impedance will be RO3 times 1 plus GM3, RO1 plus RO1. But no need to memorize this, right? This is just GM1 approximately equal to. If you forgot, right, this is so-called R out. The R out of a Cascode circuit is like the degeneration, right? So you have RO3, GM3, RO1, right? Which is approximately equal to GM-RO squared. So you did not learn anything new here, actually. You did not learn anything new. It's just that I show you that we can have a Cascode differential pair, and that's it. Yeah, we can put negative. So again, because it's a differential pair, I don't care whether it's positive or not. Yeah, but yes, but maybe I should put negative so you won't. So those students who did not come won't feel confused when they read the note. Okay, is that okay? Okay. So now we are going to a